Okay, so real quick, welcome to the MLB Statcast player pose tracking and visualization talk. Graham, do you want to go ahead and introduce yourself?
Sure. My name is Graham Goldbeck, and I'm a data quality analyst at Major League Baseball.
I'm Marc Squire. I'm a senior product manager on our baseball data team at Major League Baseball.
My name is Sethupathi. I'm an engineering manager also on the baseball data team.
So today we'll walk you through an overview of the limb tracking system. We'll walk you through the 3D visualization product that we're building, and we'll give a technical overview of how we built it, and then we'll leave some time at the end for some Q&A. Graham, go ahead.
Thanks, Marc. So just a quick overview of how the system works. So Hawkeye's tracking camera system is made up of 12 cameras. 5 are focused primarily on pitch to plate tracking and 7 on the players, but all cameras contribute to the limb tracking in some way. The video that's captured through these cameras is calibrated and run through computer vision that fits a model to the images, and then it ends up outputting an XYZ value and a timestamp. And all this data comes across in near real time, which is pretty amazing when you think about it. We used to be able to need to hook people up to mocap marker-based systems in a lab to generate anything resembling this amount of data. Think of the old videos you may have seen of players suiting up for MLB The Show and getting wired up to track all this information. And now instead we're getting it pretty much live during actual games for the ballpark. So we'll show a video of that now. So this is a clip from one of the tracking cameras. You can see there are green lines on all the players, including the umpires in the field. And you can see as they're moving, these green lines are following them very closely. This is one of a few tracking cameras focused on each of these players during the play. But you can see even the center fielder, who's hundreds of feet away from the camera, is still being followed very accurately in real time. So it's very impressive when you think about it. So now that we've seen a video of this data in action, we'll kind of see what it looks like in data form. So this is intentionally not, I didn't obscure this just to make it hard to read or something like that. This is simply one frame of output of data, of which there are 30 per second. So there are over 12,000 characters just in this one frame of data. So it's a massive amount of data compared to even the Statcast data we're used to working with. So this presents a lot of challenges in terms of data management, data distribution, storage, that type of thing. So we're constantly iterating on that to make sure we're delivering this data in the quickest way possible. So a little bit about what limbs are tracked in the system. So there are 18 points tracked in total. We start at the top, we have the ears, eyes, nose, and neck. From there, we go down, we have a shoulder, elbow, and wrist, left and right side, and then we also have the hip, knee, and ankle. So when we're able to take all these different data points and combine them to create 3D visualizations, which Marc will show a little bit more now.
Cool. So as Graham explained, the 3D visualizations use tracking data from 18 points on every player's body to create a 3-dimensional representation of actual plays from Major League Baseball games. The flexibility of the 3D rendering means that fans will be able to rewatch some of MLB's most exciting plays from angles that broadcast cameras simply can't capture. So imagine you're watching a sharply hit line drive down the third baseline, but from the eyes of the third baseman, or you're chasing down a fly ball from the center fielder's perspective, or you're standing in the batter's box watching Clayton Kershaw's curveball as it's coming in. In the future, this product will continually look for ways to leverage this next-gen technology to tell the story of baseball in compelling ways that help create deeper bonds between fans in the game of baseball. So why 3D visualizations? We're investing so much time and effort into this product because we believe it has the ability to change the game for fans, not just in baseball, but really elevate kind of the visualizations that are shown across any sport. The immersive and limitless nature of the 3D space allows us to view the game from almost unlimited camera angles, and the ability to move around in this 3-dimensional world brings the fan directly onto the field in ways that they could never have previously done before. At MLB, we're also starting to invest in a more tailored and personalized experience for each fan. So showing you more content about your favorite team or your favorite players, And when you watch a game on TV, the broadcast creates this master cut for everyone that's watching to see. While they're able to cover most of the field, an individual fan might want to see something different. And these visualizations provide a more scalable way for fans to see anything they want from virtually any angle that they want. So with that, let's dive in and see some demos here. So this is a 2015 prototype, and as many of you know, back in 2015, Major League Baseball made huge advancements in the baseball tracking and analytics space with the Statcast system. At the time, it was revolutionary, and being able to track where players moved on the field was an incredible achievement. And you'll notice all of the player paths and routes on the visualizations on this slide. You'll also notice that we're using white and yellow blobs to represent these players and where they're moving around the field. So enter 2020 and the new limb tracking system that we've been talking about here. And with 18 points on every player's body tracked, we're able to not only track where players have moved on the field, but we're also able to track and show with pinpoint accuracy how their limbs and joints moved throughout a play. As you can see, over the last 6 months, on the left-hand side is where we were at in September. On the right-hand side is where we're at right now. We've been able to make tremendous progress over this last 6 months, going from simple stick figures with kind of a bare bones, grayscale stadium to real humanoid figures with MLB jerseys and playing in kind of a more real life-like stadium with grass and dirt and those sorts of things. So as I mentioned earlier, these new 3D visualizations will allow us to see plays from impossible camera angles. And in this video, you'll see just 3 of the many possible camera angles that we're really excited about.
Looks to second, fires wide, but get the out at second.
So one of the most natural places that we see these visualizations, initially fitting in is on the live broadcast. So whether it's MLB Network talent that's breaking down a specific play or showing a play that happened earlier in the game during a live broadcast, we think these visualizations will provide an amazing new perspective to help showcase the talent of our players. And so I'll show you an example of how we see these potentially fitting in, in a live broadcast setting.
And I mean, we're talking about Statcast today. I mean, these are the plays that are so much fun to pull up the play, see how fast someone was running, how fast did he throw the ball, all of that kind of stuff. And those kind of plays really, give us some fodder for that.
So let's go through this now. This is earlier in the series. Statcast is powered by Google Cloud.
Yeah, and this was on Tuesday when they doubled off Trey Turner twice. That first throw, 83.5 miles an hour. And this is just how hard it is to get Trey Turner. I mean, we're talking about a guy running so fast, and these plays happen at lightning speed. So just even having gotten him the other day, really impressive.
And that's been a problem for him, the walks. And there it is, 4-pitch, free pass for Renhefo to start the 6th. All right, so Statcast, powered by Google Cloud. Look at Shohei Ohtani take off and pick up the stolen base. 28.4 on the sprint speed. Well, he can also swing the bat. And he's among the best in loud contact in the league, almost 110 miles an hour with that base hit.
That was very similar to an inside the park home run we saw shown earlier by Jose Altuve. Kind of in that same spot over by that 404 sign. George knew he got it good, just didn't know how good. Again, good hustle by George. And he turned it on, didn't he?
And Omar an aggressive send too, because I agree that relay throw got away.
Well, you can't anticipate that, but if he's not sending him right,
And I mean, we're talking about Statcast today. I mean, these are, and I mean, we're talking about
Come on,
Statcast today. I mean,
sorry.
these
Having trouble getting to the next slide. Cool. So additionally, we think these visualizations provide new ways for coaches to actually break down plays for their players. So whether you're a little league coach, a high school coach, or potentially, even in the majors, some of these like drone cam views that we've shown can really show how players move around the field, both in direct and indirect reaction to where the ball is hit. So for example, here, you'll see the ball, ground ball up the middle to the center fielder, and you can see where all the players are moving in reaction. So, you look at the pitcher here, he gets the throw, cuts it off, and then throws back to the second baseman. So you can really kind of show where you're supposed to move in reaction to where the ball's hit. And again, similarly, ground ball over to the right fielder, he picks it up. You can see where the players move, the cutoff throw, over to second base. So we're excited about the potential applications to teach and coach as well through this sort of tool. So with that, I'll pass it over to Sid, who's going to walk us through some of the technical aspects of the 3D visualization product. If I can get past this video here. There we go.
Thanks, Mark. So the product that Mark showed is built entirely in 3JS. 3JS is a JavaScript library that helps render 3D graphics using WebGL. It's a pretty popular JavaScript library. NASA just used it for their Perseverance simulation landing a couple weeks ago, and then we also at MLB use it for several of our products. Baseball Savant, the Home Run Derby, and then also the 3D Pitch Tracks projects both use 3JS. Since the web app, we use React. React is sort of our go-to web framework at MLB. It's a declarative component UI that makes it a lot easier to write complex web front ends. We also pulled in a new library called React 3 Fiber, which is like React being a declarative way to describe a component UI. React 3 Fiber gives us a declarative way to describe a 3D scene graph, and it makes sort of 3JS primitives a little bit easier to reason with. And then around that, we have lots of APIs deployed in Google Cloud Platform to one, serve the copious amounts of data that Graham talked about, but then also do things like rendering out visualizations in the video. Next slide, Mark. Great. So one of the challenges that we faced in doing this animation project was how do we map player movement from the discrete data points that we have access to? So again, as Graham showed, we have 18 points on the players, and in those earlier prototypes, the way we were visualizing a player was just drawing joints in between these track points. And you get a rough silhouette of the player, but it's not really that humanoid figure that we're kind of shooting for. So on the right side, what we're trying to get to is more of an animation model that's driven by an armature, and that armature is sort of a rigid structure. So our challenge is, how do we get from our track data points into driving this armature? So Mark, if you go to the next slide. The solution we kind of came up with and targeted was inverse kinematics. So in computer animation and graphics, a lot of use cases for inverse kinematics, but also in robotics, it's very heavily used. And I think it's a little bit easier to understand the problem coming at it from a sort of a tangible robotics idea. So in these two images, we've kind of shown a robot, pretty simple robot. It's got 4 links and 4 joints. And at the end of the robot, there's a claw, which we'll call the end effector. And essentially what kind of the root problem of inverse kinematics is, if we know where that end is supposed to be, how do we come up with the joint angles to drive that robot to get our end effector into the right spot? So if you imagine, if you move joint 2, joint 3 and joint 4 will also move, and there's some combination of joints that'll get our robotic arm to be in the right spot so that you can say, pick up an object in an XYZ coordinate space. So Mark, if you go to the next slide, you'll see that we have sort of a similar problem with our model that we want to move, right? So it's like how we have a robot in the previous slide, you can kind of see that there's a similar tree structure with our model where it starts at the waist. We have our lower left side sort of figured out with our hip and our knee and our ankle joints. And then on the top half, the same thing, you have your shoulders. And sort of all those things drive based on this tree of joints. Now, the one thing that's worth mentioning is we have a bit of an easier problem to solve because we actually have track data points for most of our joints. In the robot example, we only knew the location of that last end effector location, and we have to then sort of derive the intermediate joint values. Whereas with our track data points, we have all the intermediate XYZ locations. So really all we need to do is just solve our individual rotations and make sure we cascade that rotation down the chain as we sort of build out our kinematic model. So Mark, here on the next slide, here's some pseudocode. The actual code is a little bit more complicated, but I didn't want to bog down the slide. If you have any questions about it, feel free to reach out afterwards. Happy to go through some of the 3GS functions that we found most helpful. So starting out, we start out with bones in the tree and we traverse through that tree. And at first we'll take our tracking vector, which is the bone representing our tracking data. So for imagine our left shoulder, it would be our elbow and our shoulder joints. So elbow would be the end, shoulder would be the start. We find that vector in our tracking data, we normalize it so we get the unit vector, and then move on to the actual rig bone and do the same process. So in our rig, we find the elbow and then the shoulder, calculate that vector, normalize it to the unit vector. And now the next step is how do we find the rotation to get from our rig vector to our tracking vector? We use quaternions, one because 3GS has good support for them, and a quaternion from a mathematical perspective is a complex number. It's like more complex than the complex numbers you're probably used to working with. I'm not going to get into the weeds of the math because I really don't understand most of it, but from an applied math perspective, it's very useful for describing rotations because it does a lot of things. One is it's very useful for computer interpretations of rotations. The other format is Euler angles, and that's a little more human readable, but there are issues in computer animation with Euler angles that will result in something called gimbal locking, which means you can only rotate in certain axes. So quaternions solve some of those problems for us. And again, 3GS has some really nice helper functions to work with quaternions. So in this case, we'll use our quaternion library to basically find the rotation that takes us from the rig's tracked location to our tracked data location. And once we have that rotation, we set that rotation on the bone, and then we traverse to the next bone itself. Now you're probably wondering, in the robot example, each one of those joints was sort of in its own local coordinate space. And if you moved joint 2, you're also moving joint 3 and joint 4, so those are being affected. And we haven't really accounted for that in this example. So Mark, if you go to the next slide, you'll see what we do is we apply the inverse of the parent's rotation to the tracked data. And what that does is it gets our two vectors in the same local coordinate space. And that way, when you find the rotation from our rig's vector to our tracked vector, we then have a nice tight rotation that makes sense in some coordinate space. And that's what will help cascade down the whole process. So if you go to the next slide, Mark, here's a small example of how this kind of plays out. From our tracked data, we then have the ability to go from tracked discrete XYZ coordinates to a posed model. Now, there are some things that I didn't really cover in the previous pseudocode, but the intuition still follows. One of those is head pose. So if you think of like a head, the way I described it, you'll get the tilt correct. But one thing we haven't accounted for is how the head sort of turns. So to do that, we have to also use more data points like our ears that we have in the track data model that then allow us to get that rotation. And then if we apply the rotation and the tilt together, we'll then have a nice head pointing in the right direction. So with that, that's kind of the whole technical side of things. I think that's when we'll open it up to questions.
Thank you, Sid. I am trying to get the, I might have to exit. I can't get the Q&A to pop up, so let me stop sharing real quick. Oh, there we go. Okay, so Alyssa said, do different arm slots equate to different mechanics and overall velocity?
I think that might be for the last presentation.
It might be, yes. Is there a current or future direct, oops, hold on. Yeah, Christopher said, is there a current or future direct purpose the umpires are being tracked for?
So I think on that one, the way the tracking system works is it tracks whatever it sees in the field, and then we assign who that person is afterwards. So the umpires are kind of a bonus side effect of that, but they are also are part of the scene. As you can see, if we look at 3D visuals, like the umpire being there, their reaction to stuff, I think is pretty valuable information.
And then Nathan says, is the outputted data entirely unstructured, or is there at least some structure to it, like JSON?
Yeah, it is a JSON format with a bunch of different arrays and different values in it.
Christopher says, what is the best way to identify clusters / density of batted balls? Any statistical methods that help us deduce findings to one number?
That also sounds like a different presentation.
Okay. All right. Phil says, is fan engagement actually the primary focus? What about the implications for teams, both in the dugout and front office? I have a hard time believing that fans are the biggest force driving this work in 3D unless teams already have access to the 3D technology. So yeah, I mean, I think definitely one of the aspects of it. I think there's multiple aspects to this. One of the big ones that we are trying to get at is fan engagement. So providing new ways for fans to visualize the game and see the game. We're still trying to figure out how this will resonate with fans and if it will resonate. But so far, some of the user research that we've done has indicated that fans are excited about some of these new camera angles and being able to see these visualizations. Graham, I don't know if you can speak more from the club aspect. I know they are getting some of this data already, though.
Sure. Yeah, clubs do have access to this data, and we do think it has some values there. There are some limitations, though, with right now the camera's output data being at 30 hertz. The arm is moving so fast at certain parts of the throws and things like that, that you may not want to ascribe too much to that. We are considering also in the future possible higher frame rate cameras that would help some of those issues.
Are the visualizations from non-existent camera angles accurate enough to be used for replay review? So, I think Graham can speak a little bit to this, but no, the short answer is no, they're not accurate enough. We don't track fingers and feet quite yet. So I think, even still, there'd probably be a little bit of hesitancy to use them in replay reviews. But Graham, I don't know if you have any more to add on that.
No, I think you covered it all.
Cool. With the growing use of VR, do you see this coming to consumers via Oculus or smartphones? I think certainly potential use cases. I think we're very much in the infant stages of this project. So we're kind of starting small and we're going to see where it grows. But I think, those are definitely two applications that would make sense.
We've done some spikes on trying to get this onto VR and even just AR applications using ARKit for iOS. There are, again, as Marc said, very early stages, but that's definitely a longer term goal we're focusing on.
So Tim asked, with the amount of data processing this technology takes, how can this technology be implemented at an individual level, assuming that fans do not have the technology to run this product? Sid, do you think you could speak a little bit to that?
Yeah, so for the first pass, a lot of this is being rendered out into video. So as Marc said, we'll find ways to personalize content, but then also produce it in a way that can be consumed sort of at any M-level consumer device.
So Christian's asking, do you believe that this equipment will make its way into the amateur side of things, specifically big name high schools such as IMG Academy? I'm assuming that maybe that's the tracking cameras and tracking system. So Graham, I don't know if you have any insight into that.
Yeah, we're not familiar yet with if these schools are using this type of information, but from what we've seen in the past, I wouldn't be surprised if in the coming years that does make its way down to that level.
What are some of your hopes for these 3D visuals in the future? How do you plan on improving the capabilities? Yeah, so I think our hopes are that we can provide new ways for fans to connect with the game, or new ways to kind of showcase just how difficult the game of baseball can actually be. And so I think, like we said, we're still in the early stages, and I don't want to reveal too much about what the future holds, but I think there's some really interesting things that we are kicking around that we want to validate and test and see if there are some really interesting capabilities down the road that we can leverage for fans. What are some of the reasons for using Three.js versus Unity or Unreal Engine for the virtual environment development?
Yeah, that's a great question. The easy answer is we had expertise in 3JS when we started this project. Eddie Elliott, who's our lead developer on this, helped develop a lot of the 3JS projects you see on Savant, like the home run derby and the pitch 3D tracks. So that's sort of why we took this first approach. We aren't opposed to looking at Unreal or Unity to sort of render these out, but for now we're starting with 3JS. Another reason is we've also seen with past engineering projects, we get a lot of wins by having sort of tools built for internal use case really fast. For example, the film room project that launched last year was kind of born out of an internal hackathon for just generating video and showing video locally. So 3JS is very accessible. Like any browser that's WebGL compliant can use 3JS. So by building in 3JS, we're able to expose our visualizations to end users a lot faster than if we had to go down the Unreal Unity route.
Will this be available on Baseball Savant, or do you have any plans for how this tech can be accessible to the public beyond broadcast? So the short-term answer for that is these will, the actual ability to move around the field and stuff will not be available right away to the public. Right now, as Sid mentioned, our plan is to launch these as videos, and potentially in the future we'll open something up for fans to kind of play around with, but there's been no official discussion of opening that up quite yet. Sid, can you explain a bit more about the process to develop the code to track player limb locations?
So all that code actually it comes from Hawkeye. So I don't know, Graham, if you have a little bit more insight on that.
Yeah, I think probably it'd be better to reach out to Hawkeye for more specifics on that.
Cool. How accurate are your point locations from the cameras? Are there times where you need to recognize the data is bad in an instant and your animated reconstruction doesn't make physical sense?
Yep, there's still some cases of just a frame or two being off. So we do have sort of checks in place to render the correct thing out, whether that means we throw away some bad data and interpolate it or apply some different constraints. And again, if you want to speak more about that.
No, I think that covered pretty well. Like we're constantly working still on refining our process to make sure we capture these things when they do occur, but they're fairly rare from what we've seen.
Can the 3D graphics be used for reviewing a play? I think we kind of addressed this already, but the short answer is probably not right now. You mentioned rotation of the head can't be tracked. Would this apply to the rotation of the rest of the body, for example, the spine and trunk rotation?
So the rotation of the head can be tracked. In the pseudocode, it wouldn't render as a rotation. So the rotation of the head is tracked because we have sort of the stem of the head. If you think about it from like the bottom of the neck to the middle of the head joints we have, but then also with our ears, we can pose the rotation. But great question. We do the same process for rotating the torso. So just like we are able to place the spine using the hip and the neck joints, we also use the shoulder joints to give the model more of a rotation so that when they swing through the bat or throw the ball, you actually render that rotation correctly.
Do the players have to, yeah, okay. So do the players have to wear things? How do you have 18 points like ears seen by the camera?
So yeah, as was mentioned before, they don't have to wear anything. We have this model that's fit to the image it sees. So it's a entirely markerless motion capture system.
Cool. And I guess, Graham, this one's for you as well. Would those joint angle data be available publicly?
As of right now, we don't have plans for that. Right now, this data is limited to clubs and the people within the league, but it's something we do think about in the future.
Cool. One question about what do you mean by personalization to each fan? Yeah, so like the goal for us is to create a more tailored experience for fans. So when you come to MLB.com, if you're logged in and we know who your favorite team is, who your favorite players are, we want to tailor the content that you're seeing more about your favorite team and your favorite players. And so, creating that more personalized experience across all of our products. Does this also track base coaches?
Yes. As was mentioned before, similarly, the system tracks anything it sees in the field, and then we're able to assign who it was after the fact. So those people are tracked as well.
Is there a desire to eventually make the characters more realistic? So one of the things that we're currently working on is, jerseys, names, and numbers. And I think that'll add, obviously the prototypes that we showed you were just using one team's jersey and one player name. I think, it's a slippery slope getting photorealistic. So our plan right now is to not really dive into the photorealism, but more so, focus on the actual gameplay, and use kind of generic humanoid figures with the correct name on the back, the correct number on the back, and the correct jersey. I have a couple more questions here. Scott, how are we doing on time? Can I keep going here?
Yeah, go ahead. Get through a couple more.
Okay, cool. Have you resolved axial rotation such as forearm pronation or hip rotation when there's a lack of non-collinear point, i.e. extended arm or leg in your inverse kinematics model?
I can take this. No, it's actually a limitation of our data. So for the animation itself, the only rotations we can sort of handle are when we have enough data to derive that axis of rotation.
Do you have 3D models from a pitcher's view of things, specifically the pitch that is thrown? So yeah, like I said, we have the ability to kind of move around that 3-dimensional space. And so if we wanted to position the camera right behind the pitcher's head, as they throw the ball, we can certainly do that. Could this technology be used with ticketing sites to show how a home run would look from a particular seat? It certainly could. I think that's definitely a real world application for something like this. Absolutely. If it tracks base coaches, are there plans to create a way to evaluate third base coach decisions and the percentage of times that they are correct when sending a runner to home? Graham.
Yeah, I think you could probably already do that without this data set, but surely wouldn't hurt to add this to that factor.
Sure. Do you think this would lead to better marketing for the sport? Will leading towards more individualism in baseball? Yeah, I mean, I think it certainly could. I think we're gonna make a pretty big push on this product come this season. So we'll really, there's a bunch of young stars that we want to really visualize them and their talent and their abilities, and kind of showcase that. And I think we'll certainly use this product to do that. I think that's all the questions.
Awesome. I've got one of my own if you guys don't mind.
Sure.
And maybe to an extent you already answered this, but one of the things that I always think about when you guys are sharing new Statcast features and innovations is about future research opportunities. And one of the things that this struck me that it could open up is more of how the NFL has all 22 film, where they're giving you that bird's eye view of everybody moving on the field and how they're moving. So, I guess I'm just curious, what do you think that, even if it's not open to the public, what are some of the ways that you may cross-tabulate that information with other information, such as the ability to show how a team defends a given batter based on the count and things like that?
Yeah, Graham, do you have any? I don't know if you have any insight into that one in terms of the cross tabulation type stuff.
Yeah, I think we're still pretty early on the development of that, so we're not exactly sure how to use it in that form yet, but it's definitely something we're thinking about for sure.
Yeah, and I think certainly from that coaching aspect, that's one of the camera angles that we're most excited about, just because we've never had anything like that before. The ability to just see where everyone's moving, watch their paths as they're moving around the field. So certainly something that I think you'll start to see on-air talent start analyzing different plays you know, you know, the different kind of outcomes and how the shift is working and those sorts of things. So yeah.